In this video, we are going to be learning about implicit differentiation. Implicit differentiation is an application of the chain rule when you are given an implicit function rather than an explicit function. An explicit function are ones we're used to where y is isolated. So for instance, like y equals 2x plus 5. An implicit function is one where y is not isolated, and we're going to particularly see some where it would be quite difficult to isolate the y. So maybe like x squared plus y squared equals 5. When we're doing these problems, we are still going to differentiate with respect to x. So the key idea here is when you are differentiating terms with y, that means when you're taking the derivative of any term that has a y, you're going to apply the chain rule where y prime is basically dy dx. Your goal in these questions is to solve for dy dx. Okay, so we're going to take a look at some examples of various levels of difficulty here. Okay. All right, let's take a look at number 1. We are going to find dy dx for 3x squared plus 2y equals 9. So this is an example of an implicit equation because we don't have y isolated, and we are not going to isolate the y either. We're going to leave it like this. And we're just going to take the derivative. The derivative of 3x squared, we know how to do that already using power rule. That's 6x. The derivative of 2y. Okay, think about this for a moment as if that was a 2x. You know the derivative would then be 2. But since it's a y value here, rather than an x, we have to multiply by dy dx. And then over on the right, the derivative of 9 is 0. Let's talk for a second before I go on as to why that derivative of 2y is really coming out to be 2. Okay, why that's the derivative. Okay, and actually I really mean here 2 dy dx. So let's pretend for a second we had 2 times sine x. The derivative of that would be 2 cosine x. We're basically taking the derivative of whatever is after that 2. Okay. So again, that's a very similar idea here. If I have 2x, the derivative is 2. The derivative of x is really 1, and that's why we get that 2 in there. Okay. And again, you could think about it like it's some unknown function, and you'll see in the next example when we have a y squared, how that will impact things too. All right, our goal is to solve for dy dx, so I'm going to move the 6x to the other side, divide by 2, and I have dy dx is equal to negative 3x. All right, let's take a look at a much harder example here. So number 2, find dy dx for 5x minus 6xy equals 2y squared. There's a couple of reasons this problem is going to be harder. First of all, there are 2 terms that have a y. Okay, so look at the equation. Notice there's 2 different y values. And over here, I really am going to have to apply the product rule because I have 2 functions being multiplied by one another. So what I'm going to do is I'm going to think about this as the product of 2 functions, 6x times y. All right, now that we've kind of established that, let's take our derivatives. The derivative of 5x is simply 5. Okay, if there's no y term, you're going to take your derivative the way you normally would. Minus, and now we're going to find the derivative of 6xy using the product rule. So it's the derivative of the first function, so the derivative of 6x is 6 times the second, plus the first function, 6x times the derivative of the second, that's dy dx. And over here on the right, the derivative of 2y squared is going to be 4y dy dx. Okay. Just like I explained on the previous problem, let's talk about that for a second, how the derivative of 2y squared is 4y dy dx. I'm going to relate it to an example I showed you above. So let's say that I had 2 sine of x squared, and I was going to take the derivative. Well, I would bring the 2 down, and I'd get 4 sine x. But I would have to use chain rule here. I'd have to take the derivative of the inside times cosine x. Okay, so let's talk about how this relates to one another. The 4 stays the same. We're bringing that exponent down. We're subtracting 1 from the exponent. And then we don't know what the derivative of y is, right? So we don't know what y is equal to, so we just say dy dx. So this is the derivative of y, or that inner function. All right, back to the problem that we're actually working on here. I'm going to simplify this by distributing the negative, getting rid of some of these parentheses too. And remember, our goal is to solve for dy dx. So I'm going to get the two terms with dy dx on the same side of the equal sign. That means I'm going to be adding that 6x dy dx to the other side. Over on the right, I have 2 dy dx's. I need to get that to be 1, so I'm going to factor out dy dx. And now I can divide by that missing piece, that 4y plus 6, in order to isolate the dy dx. So my answer is 5 minus 6y over 4y plus 6 is equal to dy dx. Okay, number 3, a trig one. Find dy dx for sine y equals x. Sometimes people think the trig ones are going to automatically be harder. That is not necessarily true, because the derivative of sine is simply cosine, right? We've learned that before. So I'm going to take the derivative of sine, which is cosine. We keep the inside the same. Think about chain rule. And we multiply by the derivative of y, which is dy dx. Over here, I get 1. Solve for dy dx. I'm just going to divide cosine y on both sides, and I get 1 over cosine y as my answer. Keep in mind that not that we need to simplify it here, but that is also equivalent to secant y. So if you were looking at a multiple choice question, just know that those are the same. Okay, number 4 is a little different. It says find dy dx for 3y e to the x equals 9 at 1, 3. So we're finding the slope, dy dx, at a particular point, basically the slope of a tangent line here. So I also noticed that I have a product of functions, so I'm going to have to use the product rule. Okay, so let's set up our product rule here. So the derivative of the first term is 3 dy dx times the second plus the first term times the derivative of the second. Derivative e to the x is just itself, equals 9. That derivative is 0. And I'm just going to simplify this slightly. I'm going to just rewrite this without all of these parentheses. And we want to solve for dy dx. So I'm going to start by moving the term without dy dx to the other side. And then I'm going to divide by 3 e to the x in order to isolate the dy dx. These 3's are going to cancel out. And over here, we have a lot of stuff that can cancel out as well. These 3's are going to simplify to 1. The e to the x's are going to simplify. So I have dy dx is equal to negative y. What is our y value? So our y value here is 3. So we're going to plug that in. So I get dy dx is equal to negative 3. All right, our last question, similar to the previous one, we are going to evaluate the derivative at a particular point. All right, keep in mind when we take our derivative that when we're looking at radical x, we have x to the 1/2. That's what it looks like with a rational exponent. So taking the derivative, I'm going to get 1/2 x to the negative 1/2. The derivative of y squared is 2y dy dx. The derivative of 17 is 0, so I'm going to leave that part alone. Over on the right, I have product rule again. Remember, x and y are both functions, so we have to use the product rule. The derivative of the first term, x, is 1 times the second plus the first times the derivative of the second. All right, let's clean this up. We have 1 over 2 radical x when I simplify that, plus 2y dy dx equals y plus x dy dx. All right, let's get the dy dx's on the same side of the equal sign. It doesn't matter which way you move it, but we want to get them on the same side. So I'm going to choose to move the x dy dx over to the left. And you'll see I have one more manipulation to do. I've got to move that 1 over 2 radical x to the other side. Okay, we want all dy dx terms on one side, anything without dy dx on the other side. Similar to another problem we saw in this video, let's factor out the dy dx. And now we're going to divide to get dy dx by itself. I'm just leaving this as a complex fraction here because this problem is asking us to evaluate at a point. So we're evaluating at the point 9, 4. So I need to take those values and plug them in here. So at 9, 4, dy dx is equal to y is 4 minus 1 over 2 radical 9 over, in the denominator, 2 times y, so 2 times 4, minus x, so minus 9. Okay, let's simplify this. So this is 4 minus 1 over. That denominator is really a 6, right? Radical 9 is 3, so 2 times 3 is 6. This denominator is negative 1. If we get common denominators on the top, I'll just do that off to the side here. If I have 4 and I need a denominator of 6, this is going to give me 24 over 6. So this is 24 over 6 minus 1 over 6 over negative 1. 23 over 6 over negative 1, or we could just put that negative in front. You could have done that a couple steps ago as well. And I get my answer to be negative 23 over 6.